Mining. It's a silent foundation of our modern world, isn't it?
Absolutely.
Supplying, everything from the metals in your smartphone to the energy that powers our homes.
Yeah, it's fundamental.
But beneath this essential industry, there's a complex, often overlooked web of environmental and social impacts.
A very complex web, definitely.
Here at The Deep Dive, our mission is simple. We take your sources, your articles, your research, and give you a shortcut to being truly well-informed.
Cutting through the noise?
Exactly. We dig out the surprising facts, challenge common assumptions, and we aim to make even the densest topics genuinely captivating.
And hopefully understandable.
Today, we're taking a deep dive into the extensive range of environmental and social concerns commonly associated with mining. We're drawing from detailed research that highlights both the obvious and the hidden impacts. Our mission, to unpack these issues, understand their true scale, their longevity, and the challenging questions they pose.
And you've hit on a crucial point there. The sheer breadth of this topic is immense.
Right.
The concerns are incredibly varied, touching not just the physical environment, but also the social fabric, economic health, and ecological balance around mining operations. It's a lot.
Okay, let's start with the physical footprint then. The sheer scale of how mining transforms our planet is, frankly, staggering.
It really is.
We're talking about visibly reshaping entire landscapes.
Indeed. Open pit mining and what's often called mountaintop mining visibly alter topography.
Right.
They don't just create massive pits, they also build new hills and terraces from the waste rock and tailings. These aren't minor adjustments, they're geological scale interventions that fundamentally change the lay of the land.
And that visual intrusion alone can spark significant controversy, can't it?
Oh, definitely.
I'm thinking of the Pilbara region in Western Australia, where modern mine planning actually aims to retain perimeters of mesas.
Trying to mitigate the visual impact.
Trying to keep some of the original landform intact, at least from a distance. But these physical changes are far more than just aesthetic concerns, aren't they?
They absolutely are. These physical alterations create persistent long-term problems related to structural stability and safety.
Stability, okay.
You can have potential downstream impacts from erosion, mass wasting, that's the large-scale downhill movement of rock and soil, or even structural failures leading to uncontrolled contaminant releases. It's a very serious engineering challenge that can linger for decades, long after mining ceases.
And there's perhaps no more sobering example of this long-term legacy than the Berkeley Pit in Butte, Montana.
Oh, the Berkeley Pit, yes.
This enormous pit, constructed 1955, operations ceased in 82 after extracting, 1.5 billion tons of ore?
Staggering amount.
Reaching a final depth of about 600 meters?
Yeah.
What happened when they finally stopped operations there?
When the groundwater pumps were shut down in 1982, the pit began to fill with highly acidic water. Its pH is less than 3.
Less than 3.
Wow. And it's loaded with large quantities of dissolved heavy metals. This created what we now know as the Berkeley Pit Lake.
And it led to that infamous, just tragic incident in November 1995.
The snow geese.
When approximately 350 migrating snow geese landed on, drank from, and died in that toxic lake.
It's a stark illustration of the dangers. Today, the Berkeley Pit Lake is the U.S. EPA's largest Superfund site.
The largest.
Yes, and it's been called the #1 environmental hazard facing the USA today. There's even a long-standing concern that the water will eventually spill into the Silver Bow drainage system.
There's a quote from the director of the Montana Environmental Information Center back in '94 reflecting on a court ruling. The decision means you fill up a hole when you get through mining. There will be no more Berkeley pits.
A powerful statement. Learning from past mistakes.
Recognizing the permanent nature of these impacts.
Precisely. And beyond the pits themselves, the very act of land clearing and earthworks associated with mining often leads to severe water erosion. Yeah. This degrades aquatic habitats through increased turbidity, meaning the water gets cloudy with suspended particles.
It makes it murky.
Which can then smother organisms and makes the water toxic due to oxidized sulfide minerals.
There was a revealing anecdote, wasn't there? From the Grasberg deposit.
Ah, yes. Back in the early 1990s when a tailings river overflowed.
What happened?
Company officials initially tried to blame a logjam, but environmentalists immediately pointed to increased sediment loads from the tailings disposal.
So a dispute over the cause.
Exactly. That dispute ultimately led to the construction of extensive levees along the river. It really showcases how critical it is to correctly identify the root causes of environmental issues.
And the differing perspectives often in play.
Absolutely. And speaking of physical stability, slope failure is a significant concern in mining,
Right.
both for the excavated cut slopes and the fill slopes from dumped waste materials. Maintaining geotechnical stability, the structural integrity of the ground and slopes, is critical.
Why is that?
Because fill materials are often less dense, weaker, and absorb water, which can trigger collapse, especially if they chemically decompose over time.
And unfortunately, the Grasberg mine provides another powerful case study here.
Yes, tragically.
October 2003, after 5 days of heavy rain, a massive landslide. 2.5 million tons of rock and mud.
At the Freeport-McMoran copper and gold mine in West Papua, Indonesia.
Engineers had actually been monitoring accelerated rock movement and even moved equipment out of the predicted slide zone.
They did. Despite their efforts, they tragically underestimated the landslide's sheer magnitude and liquidity.
And 8 workers lost their lives.
Yes. It underscores the unpredictable and devastating nature of these massive earth movements, even with modern monitoring.
Moving underground now, these subterranean shifts can surprisingly even register as seismic events. How does that work?
Well, underground mining can cause mine subsidence,
Okay.
leading to sinkholes or troughs that disrupt surface water drainage, affect farmland, and potentially damage buildings and roads in developed areas.
And actual earthquakes.
We've seen a magnitude 3.9 seismic event in 2007 in Utah caused by a coal mine collapse. And back in 1995, a cave-in in southwestern Wyoming even registered as high as 5.4 on the Richter scale.
5.4. That's significant.
It is. It reminds us that what happens deep underground can have palpable effects on the surface, sometimes far beyond the mine site itself.
And then, of course, there's the loss of visual amenity. Surface mining commonly creates these highly visible scars.
Yeah, the landscapes are just altered.
That diminish public enjoyment and simply impair natural scenery. And the challenge here is that rehabilitation can take decades, right?
Decades. To restore natural vegetation, if it's even possible at all to return it to a semblance of its original state, an early, robust community consultation is absolutely crucial here. Using photos, films, or 3D animation, or even site visits to prepare communities for these physical changes is so important. When communities are unprepared, their support can quickly shift to active opposition, as was a contributing factor at the Bougainville copper mine. Transparency about the visual impact is vital.
Okay, so given the sheer scale of these physical interventions, the amount of waste generated by mining must be enormous.
It is truly staggering. Let's explore that impact.
Right.
Waste rock and tailings. That's the finely ground waste material left after processing or dominant mining waste streams.
Dominate is probably an understatement.
Perhaps. In some countries, they contribute significantly to the host country's total waste output.
Okay, prepare for a jaw-dropping statistic I found.
Yeah.
For gold and silver mines, over 99% of the extracted ore becomes waste.
Over 99%. Let that sink in.
And for copper mining, the multiplier is an astonishing 450.
450.
That means for every single unit of product, you're managing 450 units of material.
It led one author, Nevin, back in 1978 to state that mining companies are primarily in the waste disposal business, with the final metal merely a byproduct.
That's quite a statement.
It is. Disposing of such immense quantities is an enormous challenge, especially since waste management itself doesn't generate revenue.
It's a cost center.
Exactly. And these waste rock and tailings are a particular concern due to their sheer size and potential for toxic contaminants like metals, chemical reagents, and acidic solutions to degrade water and soil long after closure.
So, given that immense amount of waste, you'd think there'd be a huge incentive to repurpose some of it. Maybe using waste rock for construction?
You'd think so.
Why aren't we seeing more of that?
That's a perceptive question. Research into beneficial uses for tailings, for example, has been largely unproductive for a variety of reasons.
Like what?
Take the red mud for bricks example from the aluminum industry.
Okay.
A promising use for that waste was abandoned due to unacceptable radiation levels in the final product.
Radiation, really?
Yes, that's a truly unexpected hurdle, highlighting the complex challenges of repurposing these materials.
Beyond the rock and tailings, there are other waste streams too, right?
Yeah.
Those smaller.
Of course, yeah. Things like ash, domestic waste, medical waste, Scrap metal, batteries, oils, solvents.
Standard industrial waste, essentially.
Right. And the industry is increasingly adopting the 4R waste management hierarchy: reduce, reuse, recycle, and finally remove or dispose.
With waste minimization as the goal.
Ideally, yes. And recycling metal scrap is an interesting conundrum itself.
How?
While it's the obvious solution for huge amounts of metal waste, things like tax exemptions on imported equipment and disputes over valuing scrap or distributing earnings can lead companies to simply store valuable metal scrap at the mine site.
So it just sits there.
Sometimes, yes, it's an economic and policy challenge as much as a technical one.
Okay. In contrast to the past, though, modern landfills are better engineered.
Oh, definitely. In contrast to the poorly designed, polluting landfills of the past, today's engineered landfills at mine sites have impermeable liners and leachate collection systems.
Leachate being the contaminated water seeping through the waste?
Correct. As landfills become more expensive to build and manage properly, there is a stronger incentive to shift towards recycling or reuse, which is a positive development.
Okay, let's shift focus to our water. The degradation of water systems, rivers, lakes, even marine environments, is arguably one of mining's most significant and insidious impacts.
It's a critical area, absolutely. The nature of wastewaters is incredibly diverse.
How diverse?
You can have highly acidic effluents, say, from uranium extraction, or highly alkaline ones from alumina processing.
Opposite ends of the pH scale.
Exactly.
Yeah.
Or cyanide-containing solutions from precious metals extraction. These come from various streams: process effluent water used in the processing itself,
Right.
mine water from dewatering, which is removing groundwater to allow mining, seepage from waste areas, cooling water, and just general stormwater runoff.
Each needing different treatment.
Each presents unique treatment challenges, yes.
And then there's the particularly persistent problem of acid rock drainage, or ARD.
ARD, yes. And one particularly intriguing aspect to consider is how ARD occurs naturally over thousands of years as sulfide-bearing rocks weather.
Naturally.
Yes, but mining dramatically accelerates it by exposing and fragmenting these materials on a massive scale.
How does it work, basically?
At its core, sulfide-rich materials in mine openings, pit walls, waste rock, tailings react with oxygen and water to form sulfuric acid,
Okay, got it.
which then dissolves metals like iron, copper, aluminum, and lead, making them mobile in the water. They get carried away.
And you can often spot ARD by visual cues, right? Like yellow boy.
Exactly, those orange, red, iron, and aluminum compounds that stain stream beds, or bright blue-green stains from copper compounds. They're like environmental warning signs.
But the real kicker is its persistence, isn't it?
Its persistence is one of its most serious aspects. ARD can continue for centuries.
Centuries.
Yes, centuries after mining stops, rendering water unfit for human consumption and devastating aquatic life. Many fish species, for instance, are highly sensitive to even mildly acidic waters and can perish at pH levels below 6.
So it's a problem that literally outlives generations.
That's exactly right.
And the Berkeley Pit is a prime, ongoing example of this ARD persistence, with its pH less than 3 and all those dissolved heavy metals.
A stark illustration, constantly reminding us how long-lasting these effects truly are.
Beyond the chemistry, mining also affects the water balance.
Yes, it invariably influences the local and sometimes even regional water balance.
Wow.
Due to changes in landform, water usage by the mine, and mine dewatering pumping out groundwater. And what's often overlooked is that mine closure can also significantly affect the water balance.
Even after it stops.
Yes, leading to groundwater rebound, where the water table rises back towards its original level, and affecting newly established ecological equilibria as seen along the Erft River in North Germany.
So impacts can shift and evolve long after operations cease.
Precisely. It's not a static situation.
So it's not just land and water. Mining also touches the air we breathe and even the global climate. But there are some surprising nuances here, I gather.
Absolutely. Atmospheric pollution stems from sources like dust.
From roads,
Yeah.
tailings.
Right. Both from land transport and wind-blown tailings, especially fine-grained, dry tailings that can travel far. Then you have combustion gases from vehicles, crushers, power stations, and smelters.
And noise.
Noise pollution is also a major concern, primarily from blasting, fixed equipment like crushers and mills, and mobile equipment such as those massive haulage trucks with their often intrusive reversing alarms.
And there's a microclimate effect, too, like cities.
Much like urban areas, mine sites tend to be warmer than surrounding natural areas.
There's that.
Due to vegetation removal, exposed rock-absorbing heat, and heat from equipment. Theoretically, this could even lead to increased local rainfall, though that's complex.
And climate change. Mining clearly contributes to greenhouse gases.
Moving, breaking, and grinding rock, and from fossil fuel consumption. However, this poses a fascinating question. While mining adds to greenhouse gases, how does it also provide critical materials that enable greenhouse gas reduction in other sectors?
The paradox. Here's a powerful one. While mining has its own carbon footprint, it simultaneously produces the critical materials that enable greenhouse gas reduction nearly everywhere else.
Exactly.
Think about those lightweight alloys like aluminum and magnesium in your fuel-efficient car.
Makes a big difference to weight.
Or the platinum and palladium for catalytic converters, which drastically improve combustion efficiency and reduce toxic emissions.
Essential for cleaner air.
It even supplies materials for computer chips and electronic fuel injection systems, further boosting fuel efficiency.
Right, the tech relies on these materials.
And crucially, mining produces the metals used in grid-scale batteries,
which are vital for making intermittent power sources like wind and solar reliable for baseload electricity, the continuous minimum electricity demand.
So the net effect.
The net effect of these innovations is that fuel consumption in countries like the USA has remained essentially stable over the past 20 years, despite increased numbers of vehicles and a big increase in the number of large SUVs.
That's a truly counterintuitive contribution, something many might not consider.
It's easy to miss that connection.
And paradoxically, the amount of greenhouse gases produced per ton of concentrate usually increases over the life of a mine.
Yes, typically. Due to increased haulage distances as pits get deeper or longer, and greater depths requiring more pumping, more energy, as the mine ages, it generally becomes less energy efficient per unit of product.
Okay, let's unpack this next part. How does mining, a seemingly localized industrial activity, ripple out to affect everything from the smallest species to entire human communities?
The obvious direct impacts on biodiversity are things like vegetation removal and habitat alteration. You clear the land, you change the habitat.
Sure, that makes sense.
But what's truly compelling from our sources is this. Despite widespread concern, there is no documented evidence that any single species has become extinct as a direct or indirect result of mining.
Really, no extinctions traced solely to mining?
Not documented. Mining generally affects relatively small, discrete areas compared to, say, agriculture or urbanization. So it's less likely to cause total extinctions on its own. The major concern is actually the cumulative impact when mining is considered alongside other land use changes in a region.
Okay, so if direct extinction isn't the primary documented concern, what are the greater threats when it comes to biodiversity?
The indirect impacts often pose a far greater, more subtle threat.
Like what? Give me some examples.
Okay, we see this through several mechanisms. For instance, ships transporting minerals can introduce invasive marine species from distant ports via ballast water disposal.
Stowaways in the water.
Exactly. We've seen over 100 non-native species introduced to Australian waters this way. Then there's rehabilitation practices.
Planting things back.
But whether deliberate or inadvertent, they can introduce non-native weeds, maybe even through contaminated commercial seed supplies. And some non-native species, while maybe not invasive back home, become highly invasive in new environments.
And moving equipment around.
That too. Relocating used secondhand plant and equipment can introduce foreign soil pathogens, insects, and fungi.
You mentioned spiders.
Yeah, there was a notable case where numerous redback spiders were found when portable accommodation buildings from Australia were being unloaded at a mine site in Indonesia.
Wow.
Similarly, giant African land snails have invaded Lihir Island, site of the Lihir Gold Project, likely arriving with imported timber.
And even pets.
Even household pets can be an issue. Dogs and cats, especially feral ones, kill native birds and small animals. It's led some projects to ban them from mine sites altogether.
So lots of subtle, indirect impacts.
Exactly. Significant consequences for local ecosystems that often go unnoticed until it's too late.
Okay, moving to the social and economic changes mining can bring. It often provides an initial stimulus, right? Growth, jobs.
Economic growth, new jobs, and the promise or image of wealth. This naturally attracts people seeking better livelihoods.
But there's a but.
There is. Much of the resulting immigration is often unplanned. This induced development leads to significant social challenges. The influx strains existing local infrastructure, things like drinking water, waste management, public health, education.
And overwhelms local services.
Precisely. And it disproportionately affects communities least prepared for rapid change. It can just swamp local resources.
How can local communities minimize this rapid, unplanned in-migration if it poses such challenges? What can they do?
The key really lies in implementing appropriate workforce recruitment and accommodation policies from the start.
Thinking ahead.
Yes. Without them, communities can feel overwhelmed, as we saw in Tambra Grande, Peru. Back in 2002, the community actually voted to reject mining.
They voted it down.
Yes, due to fears of displacement and severe impacts on their traditional livelihoods like farming. It's a powerful example of community agency.
Now, while mineral wealth can provide substantial state revenues, you mentioned Papua New Guinea, getting over 80% of export earnings from minerals.
And Botswana, about a third of its GDP from diamonds.
History shows it doesn't always translate directly into broad economic growth for the whole country.
That's right.
Which brings us to a crucial concept for sustainable development: the Dutch disease.
Yes, Dutch disease.
It perfectly illustrates the danger of too much wealth managed unwisely.
That's the IMF definition, essentially. The term Dutch disease, coined by The Economist in 1977, describes what happened in the Netherlands in the 1960s after their discovery of natural gas.
What happened?
The influx of revenue from the gas boom increased domestic income and spending. Investment then shifted disproportionately to the gas sector.
Money followed the gas.
Exactly,
Yeah.
causing Dutch wages and prices to rise. This made their traditional manufacturing industries uncompetitive on the world stage, leading to a significant decline. The currency appreciated too much.
So the resource boom actually hurt other parts of the economy.
It can, yes. It's a stark warning. The risk for resource-rich countries is becoming complacent, not redirecting earnings into sustainable capital building for other sectors.
Diversifying the economy.
Right, and leaving communities utterly unprepared for mine closure, leading to economic stranding when the mine eventually closes, as they all do.
So the takeaway is,
This is why the modern understanding is that human resources count for more than natural resources. Investing in people, education, and diverse economies is ultimately more valuable and sustainable than just extracting and selling raw materials.
okay, we've covered the broad impacts of mining, but uranium mining introduces a whole new layer of complexity: radioactivity and its long-term implications.
It certainly does, a unique set of challenges.
Yeah.
Historically, reports from as early as 1546 detail miners in Germany and Czechoslovakia dying from mysterious lung ailments.
Way back then.
Yes, later identified as lung cancer, which was linked to uranium-rich ores, specifically radon gas exposure.
And modern research confirms the risk.
Oh yes, modern research shows significantly higher lung cancer risks for uranium workers, sometimes 2 to 5 times higher, or even much more, depending on exposure levels and duration.
So while conventional uranium mining is similar to other metal extraction in some ways,
The process can be similar, yes.
the ore contains radioactive elements like radium and radon, which makes the mine wastes themselves inherently radioactive.
That's the key difference. And one particularly fascinating aspect here is the misalignment between public concern and the objective risk assessment.
What do you mean?
Despite very strict government regulations and demonstrably low acute risks in modern uranium mines, public perception of risk remains incredibly high.
Why is that?
It's debated, but perhaps it's because of that visible, stringent regulation that people perceive a greater hidden danger. It highlights the hazard, in a way.
Interesting thought.
Huh.
And the environmental concerns of uranium mining are unique because of this radioactivity.
Yes. The waste streams include solid radioactive tailings, liquid runoff, and seepage, which can carry radionuclides, and airborne dust containing uranium and its decay products.
Like radon.
As well as radon-222 gas, which is naturally released from the ore and tailings, and its solid decay particles, which can attach to dust.
And the tailings are the main issue long term.
They are a huge issue. It's critical to note that maybe 5% of the original uranium, but all the radium, which is arguably the most dangerous radiologically long-term, remains in the tailings. Essentially, yes. These tailings are a complex system containing various radionuclides and potentially hazardous chemical substances used in processing.
How are they managed?
Short-term measures during operation often include covering tailings with water to reduce surface radioactivity and radon emission. Post-closure, typically 2 meters of clay and topsoil cover are applied to reduce radiation levels to near natural background.
And underground mines.
Underground mines can also use tailings mixed with cement for backfill, putting some of it back where it came from.
So, connecting this to the bigger picture, what are the greatest long-term risks from these radioactive tailings? We're talking long-term.
The greatest risks are indeed long-term. potential contamination of water systems if containment fails, catastrophic containment failures themselves due to erosion or seismic events, dispersal of radioactive dust and radon gas potentially for hundreds of kilometers?
Hundreds?
Potentially, yes, over long timescales. And significant chemical pollution from the non-radioactive components. These hazards can persist unabated for thousands of years, potentially even increasing due to erosion and neglect if institutional control is lost.
Thousands of years. It's hard to grasp.
It is.
The Wismut legacy in post-WWII Germany provides a stark example, doesn't it?
A very stark example. Uranium mining there, often under harsh conditions, caused widespread environmental devastation.
And the cleanup.
Even after production ceased, hundreds of millions of tons of radiating waste rock and uranium mill tailings remained. The estimated cleanup cost was over US $9 billion.
$9 billion.
Yes. That translates to a reclamation cost of roughly $43 per kilogram of uranium produced, compared to a market price at the time of maybe 5,100 kilograms. An immense expense just to rectify the historical impact at that one massive complex.
It makes you wonder, who will monitor these wastes in 200 years, let alone 1,000?
That's the profound question.
And who will ultimately pay for the efforts needed to contain them for thousands of years? This isn't just a challenge for today's industry. It's a legacy we're creating for generations yet to come, a truly intergenerational responsibility.
It absolutely is. On a more positive note, some modern strategies like burying tailings below the permanent water table, perhaps by backfilling mined-out pits, can greatly reduce both short and long-term risks by limiting oxygen and water ingress and radon escape.
Right. There are engineering solutions being developed. Okay, so what stands out to you after this deep dive? We've journeyed through the profound, multifaceted impacts of mining, from the visible reshaping of our landscapes and the immense volumes of waste generated, to the insidious threat of water contamination like ARD.
Which can last centuries.
And the unexpected ways mining both contributes to and counterintuitively mitigates climate change.
We've also seen how mining affects not just the physical environment, but also the social fabric and economic health of communities, sometimes with those unintended and complex consequences like the Dutch disease, where resource wealth can paradoxically undermine other economic sectors.
And we specifically examined uranium mining, which really pushes our understanding of long-term impact into geological timescales. It presents challenges that truly test our foresight and responsibility as a society.
Absolutely. The insights from our sources reveal that mining is an industry of immense scale and profound long-term implications. Understanding these nuances, the good and the bad, the complex interactions, is absolutely key to navigating our resource-dependent future effectively.
So here's a final thought for you, our listener. If mining operations are inherently finite, they eventually close. But their long-term environmental and social legacies potentially span thousands of years. What ethical and practical responsibilities do we as a global community bear? How do we ensure that today's resource extraction doesn't become an insurmountable burden for those who come after us?